Now we will talk about the driver and controller for the stepper motor. In principle, the stepper motor is an open-loop actuator. In its normal operating mode, the stepwise rotation of the motor is synchronized with the command pulse train. This justifies the term digital synchronous motor, which is sometimes used to denote a stepper motor. As a result of step side, whereas it is an incremental synchronous operation, open loop operation is adequate, at least in the theory. An exception to this may result under a highly transient condition, exceed the rate torch when a pulse missing can be a problem. A stepper motor needs a microcontroller. Okay, this is the box of the microcontroller or the indexer to generate the pulse commands and a driver to interpret the commands and correspondingly generate proper current for the pace winding of the motor. The basic arrangement is shown in this figure. Motor microcontroller is driver to make motor works, and it gives a response, and the response it will be give a feedback control, has to be sent, or we can use an optical encoder and feedback into the controller. Okay, this is broken line pad is illustrate the feedback that give it to the controller, and it's make the necessary correction to the pulse command when an error is present. We will see to the next diagram. In the P is the basic component of the driver, and we know this is the microcontroller as the controller. The output is position pulse train, and then there's a direction pulse train too, and we have a power supply in here that give it the input for the translator, and then the output of translator is fed to the amplifier, and then this is the driver block, that contain of power supply, translator, and amplifier, and then it drive a stepper motor, make it move, and then for the output of the driver is the current 2 windings for the stepper motor. And this is the schematic diagram for the driver stepper motor. In a drive module, there are several pins, some of which are connected to the motor controller or the computer driver inputs, and some connected to the motor leads or the driver output. There are the other pins which correspond to the DC power supply, and then common ground, and then and various control signal. The pin denoted by a step or pulse. Okay, this is the stepping pulse. Retrieve the stepping pulse signal from the motor controller, and this corresponds to the requiring stepping sequence of the motor. A transition for a low level to the high level or the rising edge of the pulse will cause the motor to move by one step. The direction in which the motor moves is determined by the state of the pin denoted by clockwise or counterclockwise. A logic high state at the pin or the open connection will generate switching logic for the motor to move in the clockwise direction. And logical low will generate switching logic for the motor to move in counterclockwise direction. The pin denoted as the half and full determines whether the half stepping or full stepping period. Specifically, a logical low at this pin will generate the switching logic for the full stepping, and the logical high in here will generate switching logic for a half stepping. And the pin denoted by the reset retrieve the signal for initialization of a stepping sequence. There are several other pins which are not necessary for the present discussion. The translator interprets the logical states at the step, half or full, clockwise or counterclockwise pins and generates the proper logic to activate the solid state switches in the unipolar drive. Especially for active logic signal is generated, active logic signals are generated corresponding to the A or the phase A. Phase A reserve and phase B or the phase B reverse. This logic signal activate the 4 solid-state switches in the bipolar drive, thereby sending current through the corresponding winding segment or leads A plus, A min, B plus, and B min of the motor. Other pins in more enhanced drive hardware include those for microstepping, connection of the external resistor and capacitor, and various enable or disable pins. So, the logic hardware is commonly available as a compact chips in the monolithic form. If the motor is unifilar for a 2-phase stepper, there should be 3 leads, a ground wire, and 2 power leads for the 2 phases. A bipolar drive will be necessary in order to change the direction of the current pulse winding. A schematic representation of a bipolar drive for a single phase of a stepper we see in this figure. When the 2 transistors mark A are on, okay, this is two transistor in here. The current flows in one direction through the phase winding. And when the 2 transistors mark A mark B are on, the current flow in the opposite direction through the same pace winding. What is shown is an H-bridge circuit. So the PWM, or the pulse width modulation, may be used to adjust the pace current. This is the useful of the PWM, or the pulse width modulation. And we can see from this figure the logic hardware to interpret the information carried by the stepping pulse signal, and this is the useful of the driver, and the direction pulse signal, or alternatively to clockwise pulse signal and counterclockwise pulse signal. For example, step instant and the direction of the motion. And then the driver provide appropriate signal to the switches, or the switching MOSFET, that actuate the pace winding. This is the translator unit of the drive hardware, and it's contained with the indexer of the drive system. The drive circuit for pace winding with the switching transistor to actuate the pace on-off, reverse in the unifilar case, on-off the bifilar case, and the power amplifier for the winding. And then the driver need DC power supply to power the amplifier and logic the circuitry. For the motor time constant and torque degradation, as the torque generated by a stepper motor is proportional to the pace current, it is desirable for a pace winding to reach its maximum current level as quickly as possible when it is switched on. Unfortunately, as a result of self-induction, the current in the energy space does not build up instantly when switched on. As the stepping rate increases, the time period that is available for each step decreases. So, a pace may be turned off before reaching its desired current level in order to turn on the next pace, thereby degrading the generated torque at the higher step rates due to the inductance. This is the illustration for the low stepping rate, and B in here is illustrated to the high stepping rate. This is the stepping pulse, and this is the pace current, and this is for the high stepping rate. One way to increase the current level reached by the pace winding would be to simply increase the supply voltage as the stepping rate increases. Another approach would be use a Cooper circuit, switching circuit, to switch on and off at high frequency. A supply voltage that is several times higher than the rated voltage of the pace winding, specifically a sensing element, a resistor in the drive circuit detects the current level, and when the desired level is reached, the voltage supply is turned off. And then when the current level goes to below the rated level, the supply is turned on again. The required switching rate or the chopping rate is governed by the electrical time constant of the motor. The electrical time constant of the motor is given by theta E, is it true? Tau, yes. Tau E equals to L per R, where the L is inductance of the energized phase winding and R is the resistance of the energized circuit, including winding resistance. Okay, this is for the phase winding, and this is the switching command. Fit to the switching circuit, and then it's connected to the phase winding and the power supply. So it's well known that the current built up is given by I V per R exponential 1 minus T per tau E, whereas V in here is the supply voltage. The larger the electrical time constant, the slower the current built up. The driving torque of the motor decreases due to the lower phase current. Also, because of the self-induction, the current does not die out instantly when the phase is switched off. The instantaneous voltage caused by the self-induction can be high, and they can damage the translator and other circuitry. The torque characteristic of a stepper motor can be improved, or particularly at a high-speed stepping rate, and the harmful effect of inducted voltage can be reduced by decreasing the electrical time constant. So the convenient way to accomplish this by increasing the resistance R, but we want this increase in R to be effective only during the transient periods. At the instance of switch on and switch off, during the steady period, we like to have a smaller R, which will give a large current or the magnetic field, producing a higher torque and furthermore lower power dissipation and associated mechanical and thermal problems and reduction of efficiency. This can be accomplished by using a diode and a resistor delta R. Which is connected in parallel with the pass winding. And in this case, the current will loop through R and delta R as shown during the switch on and switch off periods, thereby decreasing the electrical time constant to the tau E equals to L per R plus delta R. During the steady condition, however, no current flows through the delta R. Such circuits to improve the torque performance of the stepping motors are commonly integrated into the motor drive hardware. In a motor, the electrical time constant is much smaller than the mechanical time constant. Hence, increasing the resistance is not a very effective way of increasing damping in a stepper motor. So you can search what is a damping effect of the stepper motor. So, how to control of a stepper motor? Open loop operation is adequate for many applications of stepper motor, particularly at a low speed and in steady state condition. The main shortcoming of the loop control that the actual response of the motor is not measured. Consequently, it is not known whether a significant error is present, for example, due to the missed pulse. If a pulse is missed by the motor, the response has to catch up somehow by a subsequent overshoot in motion, or else an erratic behavior may result, causing the rotor to oscillate and probably stall eventually. Under relatively favorable condition, particularly with a small step angle, if a single pulse is missed, the motor will declare it so that a complete cycle of the pulse is missed. Then it will lock it again with the input pulse sequence. In this case, the motor will trail the correct trajectory by the rotor teeth pitch angle theta r. Here, the pulse equals in number to the total pace of P. Note that in here we have theta r is equals to P multiplied by delta r. This is the means. In this manner, it also possible to lose accuracy by an integer multiple of theta r because of the single missed pulse. Under adverse condition, however, pulse missing can lead to highly non-synchronous response or even complete stalling the motor. In summary, the missing or dropping of a pulse can be interpreted in two ways. First, a pulse can be lost between the pulse generator, for example, a common computer or controller, and the translator. In this case, the logic sequence within the translator that engine's motor pace will remain intact. The next pulse to arrive at the translator will be interpreted as the lost pulse and will energize the pace corresponding to the lost pulse. As a result, a time delay is introduced to the common pulse sequence. So the second interpretation of the missed pulse is that the pulse actually reached the translator, but the corresponding motor pace was not energized because of some hardware problem in the translator or other circuit. In this case, the next pulse reaching the translator will not energize the pace corresponding to the missed pulse, but will energize the pace corresponding to the retrieved pulse. This interpretation is termed missing pace activation. And in both interpretation of the pulse missing, the first is particularly under variable speed condition. If the successive pulses are received at the high frequency and the pace translator might not respond to the received pulse, and the corresponding pace will be energized before the next pulse arrives. And the second is because of the malfunction in the pulse source, a pulse might not actually be generated, even when the motor is operating at well below its rated capacity. So the motor will declare it because of the negative torque from the pace that was not switched off. Depending on the timing subsequent pulse, a negative torque can continue to exist in the motor, thereby eventually stalling the motor. The motor declaration due to the pulse missing can be explained using the static torque approximation. As we see in this figure, we know that there are 3 pace motor with 1 pace on excitation. Only 1 pace exceeded at the given time. Suppose that the under normal operation condition, the motor runs at the constant speed and pace activation is broke about at point A, B, C, D. Using a pulse sequence sent into the translator, these points are equally spaced, with the horizontal axis as the angle of rotation. Then the degree is theta, not time t, because of the constant speed operation. The torque generated by the motor under normal operation without pulse missing is shown as the solid line. Note that pace 1 is excited at point A and pace 2 is excited at point B, and pace T3 is excited at a point C, and then so on. Okay, a pulse is missed at B. Pace 1 continue to be active, providing a negative torque. This slows down the motor. The next pulse is received when the rotor is at the position B apostrophe, not C, because of the rotor declaration. Pulses are sent at equal time intervals for constant speed operation. At point B apostrophe, pace 2 or not pace 3 is excited in this case because the translator interprets the present pulse as the pulse that was lost. The next pulse is received at C apostrophe, and so the resulting torque is shown by broken line in this figure. As this torque could be significantly less than the torque in the absence of the missed pulse, depending on the location of the point B apostrophe, C apostrophe, and D apostrophe, for example. And the motor might declare it continuously and finally stall. In figure B, we can see the pulse at B fails to energize pace 2. So the pulse B fails to energize pace 2. This declares the motor because of the negative torque generated by the existing pace 1. The next pulse is received at the point C apostrophe or not C because the motor has slowed down. This pulse exceeds pace 3, not pace 2. But unlike in the previous case, because the translator assumed that the pace 2 has been exceeded by the previous pulse, the subsequent pulse arrives at the point not t or the t apostrophe because of the slow speed of the motor. The corresponding motor torque is shown by the broken line at this figure. In this case, as well, the net torque can be much smaller than what is required to maintain the normal operating speed, and the motor may stall. To avoid this situation, pulse missing should be detected by a response sensing, and the proper corrective action taken by modifying the future switching sequence in order to accelerate the motor back into the desired trajectory. Or in the other words, is feedback control is required. And this is the feedback control of stepper motor. It may be used to compensate for motion error in stepper motor. This block diagram for a typical closed-loop control system. This should be compared with the figure in open loop control for the stepper motor. The noted improvement in the feedback control scheme is that the actual response of the stepper motor is sensed and compare with the desired response. If an error detected, the pulse train to the drive system is modified appropriately to reduce the error. Typically, an optical incremental encoder is employed as the motion transducer. This device provides two pulse trains that are in pace quadrature, or alternatively a position pulse sequence and a direction change pulse may be provided. Given both the magnitude and the direction of the rotation of the stepper motor, the encoder pitch angle should be made equal to the step angle of the motor for ease of comparison and error detection. So when the motion comments as an input, it will be fed to the control computer. So the output is control pulse train will be fed into the drive system, and the output of the drive system will be fed to the stepper motor to make it move. And for the stepper motor give a response, and if error occur, so there's an feedback block as incremental encoder that measure a pulse train. So it will be feedback to the controller or control computer to make it fix. So the resulting closed-loop system can operate near the rated capacity, torque, speed, or the acceleration of the stepper motor, perhaps exceeding these ratings at times, but without introducing excessive error and stability problem. This is for the closed loop system. And this is the feedback encoder driven by a stepper motor. This is for the first encoder pulse, and this is for the second encoder pulse, and this is for the third encoder pulse. And we can get the delta theta S plus delta theta L is equals to 2 delta theta, okay, 2 delta theta, where delta theta is the step angle. So this is for the feedback encoder driven stepper motor, and this is the torch control drugs, the switching, and this is the effect of advancing the switching pulse. And this is for the Brook line is as the conventional switching, and this is for the advanced switching. And this is for the static torch, and this is for the this is for the broken line as the static torch, and this is for the dynamic torch of the stepper motor. The switching point, although the static torch curve takes a negative value, okay, this is for the negative value, in some region under this advanced switching sequence, the dynamic torch stays positive at all times. And main reason for this is that a finite time is needed for the current in the turn-off phase to decay completely because of the induced voltage and the eddy current effect. And for the first figure, in this case of advanced switching, the static torch always remains greater than the common torch value at the point intersection. This confirms that the intuitively clear motor torch can be controlled by adjusting the switching point. The resulting actual magnitude of the torch, however, will depend on the dynamic condition that exists. For the low speed, the dynamic torch may be approximated by the static torch curve. It makes the analysis simpler. As the speed increases, the deviation from the static curve becomes more pronounced for reasons that are mentioned before. Okay, we go to the stepper motor in industry. So this is the application of a stepper motor in equip and automotive cage in industrial machine like packaging, labeling, filling, and cutting. And then it's widely used in security device and as the security and surveillance camera for the moving step of the camera. And in medical industry, stepper motor are widely used in sample, digital dental photography, respiration, fluid pumps, and blood analysis machine and medical scanner. And then for the consumer electronics, image scanner, photocopier, printing machine, and the digital camera for automatic zoom and focus function. The stepper motor are also used in elevator, conveyor belt, and land diverter. This is the illustration of the use of stepper motor in industrial and in the medical. And then in camera for the lens. And for the interfacing with the stepper motor, rotation is proportional to the number of input pulse, and speed is proportional to the frequency of the input pulse. Quick response to the starting, stopping, and reversing, and very precise. And we can use a controller and driver to make the stepper motor works. Okay, this is the type of the stepper motor. And now we move to the advantage and the disadvantage of the stepper motor. First, the advantage: the rotation angle of the motor is proportional to the input pulse. The motor has full torque at stand if the winding were energized, and the precise position and repeatability of the movement, since a good stepper motor have an accuracy to the 3 up to 5% of a step, and this error is non-accumulative from one step to the next. So the position error is non-cumulative. A high accuracy of the motion is possible even under the open loop control. And then excellent response to starting, stopping, and reversing, and very reliable since there are no contact brush in the motor. Therefore, the life of the motor is simply dependent on the life of its bearing. And then the motor response to digital input pulse provides open loop control, making the motor simpler and less costly to control. And then it's possible to achieve very low speed synchronous rotation with the load that is directly coupled to the shaft. And wide range of proportional speeds can be realized as the speed in proportional to the frequency of the input pulse. So the torque capacity and power requirement can be optimized, and the response can be controlled by electronic switching. And because the incremental nature of the command and motion, stepper motor are easily adaptable to digital control application. And the stepper motor have the disadvantage. First is resonance can occur if not properly controlled, and not easy to operate at the extremely high speed. And there are low speed actuators, so the torque capacity is typically less than 15 Nm, which may be low compared to what is available from the torque motor. They have a limited speed, limited by torque capacity and by pulse missing problems due to the faulty switching system and drive circuitry. Must step slowly to ensure the accuracy. They have high vibration level due to the stepwise motion. Large error and oscillations can result when a pulse is missed under open loop control. Thermal problems can be significant when operating at a high speed and use the same amount of power regardless of load. It means lower power efficiency, and the torque decreases rapidly as speed increases or no internal feedback. So cannot tell the step was miss or the low torque to inertia and cannot accelerate loads very rapidly. Okay, this is the end of our material about the stepper motor. Thank you.